Hello everyone and welcome back to this tutorial series about how to create a 3D game in C++ from scratch. In this 23rd video tutorial we will talk about point light. In particular we will see how we can simulate the diffusion of light radiations radially in every direction, how to limit the diffusion of light in the volume of a sphere, and in the end, we will see how to apply a simple loop animation to our light. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to create a point light. So let's start with the requirements. We need a C++ IDE, Visual Studio is recommended, the target platform is Windows. We also need DirectX 11 SDK, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. Today our goal is to enlighten our scene with a specific type of light source, the point light. As we have already seen in the 19th video tutorial, light is an electromagnetic radiation that, when it is reflected by the surface of an object, can be perceived by the human eye, allowing us in this way to perceive and visualize the environment around us. Depending on the way in which the radiations are emitted, we have different types of light sources. We have already seen the directional light, where the light radiations are emitted in one single direction. And then we have the type of light source we will face today, the point light, where instead the radiations are emitted radially in every direction. For this fact, this type of light is commonly represented as a sphere. The last time we have seen how we can simulate the lighting of the scene through the usage of the mathematical model called the phone reflection model. Today we will use the same exact model. The only thing that will change will be the way in which we will compute the direction of all the light radiations emitted by the light source. With directional light source, this problem has been easy to solve, since all the light radiations emitted have the same already defined direction. With the point light, instead, the problem is a bit different. Let's see this image. Here we have a simple scene with some objects and a point light represented as a sphere. A point light, unlike a directional light, has a position that allows it to be placed anywhere in the scene. With this information, the direction of a specific light radiations emitted by a point light is the normalized vector between the light source position and the point of the scene in world space. As we have already seen in the previous tutorials, a vector can be computed by subtracting the position of the light source with the position of a point of the scene. This is done for all the points of the scene that are visible to the camera, in other words, for all the pixels that compose our scene. Once we have computed the light direction for a specific pixel, we can place it in the dot product function used to calculate the diffuse lighting, and also we can place it in the reflect function used instead to calculate the specular lighting. The result will be like this. But there is another problem though. Here the point light doesn't seem to be limited in the volume of a sphere, as we have seen in the previous images, but it seems to be spread in a more wide volume. That's because we are currently considering only the light direction. We have to consider even a radius for the sphere. The light radius, as the name suggests, simply indicates the size of the volume of the sphere in which the scene and the various objects are completely and fully enlightened by the light. Very well, but there is another important characteristic of light to consider: the light attenuation. Light attenuation is the gradual loss of intensity of light the farther it travels from its source. In this image, it is represented by the transition from light to dark. Good, we have seen a sort of representation of how the point light works. But how can we actually limit the light in a sphere and apply the attenuation? As first thing, we have to compute the distance between a point of the scene and the position of point light. And then we have to subtract the radius of the light to this distance. In this way we get the area in which the light attenuation can take place, that we can call fade area. At this point, as for spin, let's limit the light in a spherical volume considering the light radius. To do this, let's start to divide the final computation of diffuse lighting, that is, the multiplication between Kd, Id, and the amount of light, with a specific formula, that is 1 plus the fade area. We can call this formula attenuation. Let's try to understand the meaning of this formula. Fade area can assume different values. If the fade area is less than 0, we are currently inside the sphere, and so, in this case, we will have the full light. But if we replace fade area in the attenuation formula with a negative value, what happens? That we will divide the diffuse lighting with a value that is less than 1, and so we will get a lighting more brighter than normal, that is an undesired effect. For this reason, we will consider only the positive values. Indeed, if we now replace the fade area with 0, we will divide the diffuse lighting with 1, obtaining the correct lighting. What if the fade area is greater than 0? Well, the attenuation formula will be greater than 1, and so we would obtain a less brighter lighting, achieving in this way the transition from light to dark we have seen previously. This computation should be applied in the same way even for the specular lighting. And this is the final result. At this point, seems our point light is ready, and in some way it is. But the attenuation formula we have just used is a very basic one. It is possible to use more complex formulas. Today we will see the formula that mixes the constant, linear, and quadratic functions. This kind of formula provides more control over the light attenuation. Let's see some examples. If we use 1 for all the variables, we get nearly the same attenuation effect of the previous formula. But what happens if we, for example, set the linear and quadratic variable at 10? Well, now the effect has changed. In this case, since the light is completely focused in the sphere volume, and it is not scattered away like before. And that's all! We can tune these variables as we want to get the desired attenuation effect. Very well, we have collected all the necessary information to start the implementation. As first thing, let's go to App Windows C++ file and let's use the scene.obj model. Let's see if it works. And it works. Here we have many types of earth. Very well. let's go ahead and let's add a new filter. Let's call it shaders. Now we can drag and drop all the various shaders inside it. At this point, let's add a new filter and let's call it Earth Shaders. Here we can place the vertex and pixel shaders we have used so far. Very well, now let's add again another filter and let's call it Point Light Shaders. Here we can start to create the shaders for the point light. As for a spin, let's create the vertex shader. And then the pixel shader. Let's exclude them from build. And so far so good. The next step to do is to copy paste the code of the previous shaders into the new ones. Now let's go to App Window C++ file and let's change the previous shaders with the point light ones. At this point, we can start to implement the point light. So let's go to point light pixel shader file and as first thing, let's remove all the unnecessary textures. In the PS main function, let's remove all the previous textures color variables and let's use only one of them. Let's set it to white color for the moment. Let's restore the computation of diffuse lighting as the one we have used in the 19th tutorial. So let's remove the various ID day and night. Let's set ID with a simple white color. And let's multiply the amount of light with the various diffuse lighting component. And at the end, we have to limit our dot product to only positive values. As the very last thing, let's substitute the Earth specular variable with the value 1. Let's see if it works. And it works. We have a directional light that rotates around the y-axis. Now we can finally start the point light implementation. Let's go to App Window C++ file, and in the constant structure, let's add two new variables, the light position and the light radius. Let's set the radius to 2 and the light position at 1 along the y-axis. At this point, we can copy-paste these two variables both in the vertex and pixels shaders. So far, so good. The next step to face is the computation of light direction. To do that, as the first thing, we have to go to vertex shader and we have to get the point of the scene in world space. Since this information allows to compute even the direction of the camera in the pixel shader, we don't need to calculate it in the vertex shader. So let's remove it. Let's pass the world position to our VS output structure. Very well. Let's go to Pixel Shader and let's substitute, even here, the direction camera with world position. At this point, we have to move the computation of direction to camera in the Pixel Shader. So let's go to Vertex Shader and let's copy paste it. So good! Now we can start to compute the light direction for the point light. As we have already seen in the introduction, is the normalized vector between the light position and the point of the scene in world space. Let's place it in the dot product for the diffuse lighting and in the reflect function for the specular lighting. Let's see if it works. And It works, but as we know, in this moment the light is not limited into a spherical volume. So let's start to integrate the light radius in our computation. As first thing, let's calculate the distance between the light and the point of the scene. At this point, we can calculate the fade area, that, as we have already seen, is simply the difference between the distance between the two entities and the light radius. Very well. As last thing, let's finally compute the attenuation by using the basic formula 1 plus fade area. Now let's divide the diffuse and specular light in color for this attenuation. Let's see if it works. And it works! The light is now limited in a spherical volume with a defined radius. Very well. At this point we can use the other attenuation formula called linear quadratic attenuation. Let's add three variables: constant, linear, and quadratic. Let's set them to 1 at the moment. And let's use the same formula we have already seen in the introduction. Very well, let's see if it works. And it works. Nothing seems to be changed. So let's see what happens if we set the linear and quadratic variables at 100. Now the light seems to be more concentrated in the spherical volume, and it is not so much scattered. If we set 10 instead, the light starts to fade away a bit. So good, the point light is now complete. Let's add some animation to see the light in action. Let's go to App Window C++ file, and in the Update Model function, let's change the light position. Let's make an animation in which the light rotates around a specific point. So let's set the x-axis with a cosine function. We can use the angle we have already used for the directional light. Let's set the y-axis at 1, and finally let's set the z-axis with a sine function. Let's see again if it works, and it works, but it's a bit slow. Let's make the animation a bit more quick. Good! Now we can place the texture over the surface of our scene. So let's go to Pixel Shader file and let's sample our texture. At this point, we can go to App Window C++ file and we can start to remove all the previous textures of the Earth. Let's use only one texture that we can call Wall. Let's see if it works, and it works. Now let's set a radius of 4 units. As the very last thing, let's control the light radius through the usage of two keys. With the O key, let's reduce the light radius of 1 unit per second. And with the P key instead, let's increase the light radius of 1 unit per second. Finally, we can set the light radius in the constant structure. Let's see if it works. And it works. If we press O, the light volume is reduced. If we press the P key instead, the light volume is increased. And that's all for now, folks. Today we have seen how to create a point light. I hope you enjoyed this video. See you soon. Thanks for watching.